this is kind of a fun application of geometric series. Well, at least fun for some of us. So if you look at this question, it refers to a repeating decimal, right? 2.516516, etc. The 516 here has a bar over it. I'm not sure how well you can see it on the thing. But essentially, we have a repeating decimal here, and we want to express it as a ratio of integers, right? So it's kind of cute that we can, in fact, use the geometric series to do this, because what do I have here with the bar? So if I just break this up, that's 2, and then these 516s go together. So the first one is 0.516, right? And the second piece is 0.000516. And then the third piece, we're going to have a couple extra zeros, right? 3 extra zeros. And I keep going on and on and on like that. Right? So that's really what's happening with my repeated fraction. So let's see. That's not so easy to see what that is, or maybe it is. But if I write these as fractions now, this is just 516 over 1,000. This is 516 over, I need 6 zeros, right? And then this one would be 516 over 9. Well, not 9 zeros, 8 zeros, but yeah, you get the idea. 100,000, etc., right? Yeah, that's correct. So there we are, etc. Plus dot, 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 right? Because we're going off to infinity. So I can see here that there's some powers going on. So you can really think about this as a geometric series. So if I write it with the powers, it's a little bit nicer to look at. You can see this is going to be 10 to the 9. This next one would be 10 to the 12, etc. The 2 is separate. I'm just going to leave the 2 by itself and add it up in the end. Okay, but I want to think about this as a geometric series. I'll keep the 2 there so I can write equals. But I want to think about this piece as a geometric series, where this is A, this is AR, this is AR squared, etc. Right? So if I think about that, AR squared, AR cubed. All right, so it's very clear that my A is 5/16 over 10 cubed, right? And then if AR is 5/16 over 10 to the 6th, that's going to tell you that your R is going to be 1 over 10 cubed as well. So then I can write this as the sum from n equals 1 to infinity of 5/16 over 10 cubed, that's the A, times R, 1 over 10 cubed to the n minus 1. Okay, so now once we have it in this form, we can use my A over 1 minus R. And of course, 1 over 10 cubed, obviously it's less than 1. So this thing is going to converge. It's going to converge to A. Sorry, I'm a little down out of space here. Over 1 minus R. So I make a common denominator here. It's 10 cubed or 1,000. 1,000 minus 1 is 999. So I end up with 2 plus 516 over 999. And I can make a common denominator. I did this. If you make a common denominator, add those guys together, you have 2,514. So that's your answer. That is the ratio of integers. That if I stick that in my calculator, I'm going to be getting this. Okay? This is kind of a cute thing to do. And this is probably one of the harder ones because it's got you're repeating 3. Okay, so if I was repeating only one digit, then I wouldn't have to have a 10 cubed here. I wouldn't have to be going in pieces of 3. I would just go in tens, like 1/10, 1/100th, etc. But you see now how it works out with multiple digits. I think it makes sense most of all to first write it this way as the expansion and then try to put it into fractions. And then once you have it in terms of fractions, you want to kind of massage it into the form of the geometric series.